Hi, my name is Yuriy and I'm a math PhD student at Imperial College London, as well as a tutor at the Elite Prep. This video will be one of a series where I tackle quantitative research interview problems which are usually given to junior applicants at hedge funds and investment banks. The format of these videos is going to be an introduction to the question, as well as an introduction to the intuition. Then I'm going to give a hint so that you can attempt to solve the question on your own. And finally, I'm going to go through the problem very thoroughly, explaining all the details. While I'm going through these details, you should sometimes keep in mind that this is much more thorough than is expected in the actual interview. And a lot of the time, just a justification of the intuition is sufficient. I will make it very clear where this is the case and where it is preferable that you actually do go through the steps. These problems may be a little bit challenging at first if you haven't done any of this in the past, but I do promise that it does get easier with practice, so just keep at it. The question I'm going to be tackling today is the following. In a solo game, you have two opaque boxes. Every round, you decide whether to place or take. By placing, $1 from an external source goes into one of the boxes chosen at random. By taking, you randomly empty one of the boxes and claim its contents. This game lasts 100 rounds. Assuming optimal play, what is the expected payoff of this game? Note that you do not know how much money you have taken until the end of the game. Okay, so let's just start off with describing the problem and looking at the intuition of the problem. So we have two boxes. Let's just call them B1 and B2. In round one, we can choose if we place or take. And it's important that we randomly place into one of the boxes. And similarly, when we take, we randomly empty one of the boxes. So let's go through the following example. If in round one, we decide to place, then $1 will go into either B1 or B2. Let's just say that $1 goes into B1 for now. So that's round one. At round two, because the boxes are opaque, we do not know which one has the $1. So we do not know when we take, if we've taken the $1 or not. So in round two, again, we can choose to take, but taking may either go for B1 or B2 because we randomly empty the boxes. So our goal is to decide on a strategy for playing this game such that we maximize the expectation of our payoff of the game. So to start off with, let's look at a little bit simpler example. So what if taking was not random? So once we've placed some amount of times, we can say we take from here and then we take from here. Well, then it's obvious that we can play 98 rounds placing and then just take the value from both boxes. Because after 98 rounds, you would have X dollars in B1 and 98 minus X dollars in B2. So by taking from both boxes, you just collect all the money and be sorted. The problem is that when we take, we might actually end up taking twice. So we might taking twice from the same box. So once we take the X dollars, there's nothing else for us to take. So you'll take X, then you'll collect $0 every consecutive time that you take again from that box. So we want to avoid that scenario. So the hint, I guess, is how many times do we need to take to ensure that both boxes have been taken. So from this, I think at this point is a good time to pause and try and solve the problem on your own. If you've already done that, then we can continue. Okay, so I'm going to use the following notation. I'm going to say Tn is the value, the payoff of the game when we place 100 minus n times, and then we take n times. And we want to maximize ETN. So first, we want the strategy, i.e. n, such that ETN is maximal. And then we want the value of ETN itself. Okay. So let's just, again, start with the easiest case. What happens at t0? Well, if we don't take any times, then clearly we cannot collect any money from either of the boxes. So t0 is equal to 0. What about t1? So t1, in that case, we end up taking from one box, and there was some amount of money which was put into either of the boxes. So I'm going to write this out very explicitly. In practice, an interview, it would probably be enough giving the expectation of T1 just off the top of your head because it's quite intuitive. But I'm going to write out the random variable T1 as a function of other random variables. The other random variables are going to be DI. So DI is the dollar at round I, and also S, which is going to be the selected box. So DI is either in B1 or B2, so in box 1 or B2, and S is either 1 or 2 to denote that we've selected box 1 or box 2. So given these, we can then say that T1 is equal to S equals 1 or 2, sorry, J equals 1 or 2, I equals round 1 to round 99, because when we take once, we only have 99 rounds. 99 rounds of placing, so there would only be $99 which we place. And then we have two indicator functions. So we say that DI is in box J and S is equal to J. So this basically sums up over all the possible cases. So that's the random variable which we get from this situation. And after we have this random variable, we can look at the expectation of this random variable. So then once we look at the expectation, we can use linearity of the expectation and independence of di and s. Di and s are independent because at each step we don't depend on the previous step of which box we've placed the dollar in, and also when taking we don't depend on where the dollars have happened. So we take randomly and we place randomly, and we do that in an independent fashion. So when taking the expectation, the sums will go outside of the expectation, and we take the expectation over the indicator functions. And for those who may be unfamiliar, the indicator function di is equal to 1 when dollar at round I is in box J, and 0 otherwise. Okay. So this then becomes the sum from J equals 1 to expectation of the indicator of di in Bj. So now we're using independence, where the expectation of the product of two functions equals to the product of the expectations of the two functions. Then we use that the expectation over the indicator function is just equal to the probability of the underlying event. And then we know that since we're choosing at each step randomly either box 1 or box 2, this is 1/2. And when we're taking, we're also choosing randomly. So again, the probability that we randomly choose box J, where J equals 1 or 2, is again 1/2. So we're summing over a quarter 99 times, and then that 2 times. So we just have that this is 99 over 2. So from now on, these kind of expectations, I'm going to assume you can calculate intuitively. This could have been easier seen that after 99 rounds, you either choose one box or another box. So the expected value would just be half of the total number of dollars. Okay, so let's now extend this to the case where we have expected value of Tn. So we take n times and place 100 minus n times. This is equal to the expected value of Tn, given that in n takes, we see both boxes, and that's multiplied by the probability of this event. So I'm going to call this event n and plus the expected value of Tn, given that in n takes, we see only one box, times 1 minus probability En. So I've here used the law of total probability because in any number of takes, we can either see one box or two boxes. So we'll either have this situation or this situation, and you can decompose the probability space over these two events because you can't see both one and two boxes at the same time. You have to see either one or the other. So we have applied the law of total probability. Okay. Then we have the following. We want to figure out what probability of En is. So probability of En is equal to 1 minus the probability that we in n takes only see one box. And to only see one box in n turns of taking boxes, you need to choose either box in the first turn and then keep choosing the same box in all the remaining turns. So the way this happens is 2 to the minus n minus 1 ways. The reason for this is because each time we have a half probability of choosing that same box. And the first turn doesn't matter because we could have chosen either of the boxes to start off with. So our probability of En is equal to 1 minus 2 to the minus n minus 1. So therefore, the expected value of Tn is equal to, so if we've seen both boxes, Tn would just be the sum of all of the dollars. And at step n, we've had 100 minus n dollars. So that would be 100 minus n times, so probability of En is 1 minus 2 to the minus n minus 1. And then plus the other part. And the other part, the expected value, if we only see one box, would be half the total amount of dollars. So we would have 100 minus n over 2 times 2 to the minus n minus 1. So that 2 to the minus n minus 1 came from this came from this, and then we computed the other the conditional expectations by getting these two. Okay, so then we have that this is equal to 100 minus n, 1 plus 2 to the minus n minus 2 to the minus n minus 1. Which is equal to 1 minus 2 to the minus n. So then the problem becomes to maximize this. In order to maximize this, the easiest way is to, in essence, see at what point we go from increasing the function to decreasing the function. So intuitively, if we plot these values of Tn against n, so n being the number of takes. When number of takes is 0, we have 0. We're going to reach some maximum at some point and then decay after that. So we want to find this maximum. And to find this maximum, it's enough to look at ETN versus ETN plus 1. So what happens if we do one more take? We want to get to the point where doing one more take actually reduces the probability. So we want ETN to be greater than ETN plus 1. Okay. So then we just substitute the results we got above. So 100 minus n, 1 minus 2 to the minus n is greater than 99 minus n, 1 minus 2 to the minus n plus 1. So this is the same as which is the same as and this happens when n equals to 6. So then, just as a sanity check, we can consider expected value of T5, expected value of T6, and expected value of T7. So recall the formula, we had this. So in T5 we have 95 times 1 minus 2 to the minus 5. That's equal to 95 times 31 over 32. This is around 95 minus 3, because this would just get rid of, 32 is around 1/3 of 95, where 97 is around, ET7 is around, so 93, 1 minus 2 to the minus 7. That's equal to 93 times 127 over 128. So that's again around 92, because this is around 1. So this is almost like taking 1 away from 93. And finally, we have 94 times 1 minus 2 to the minus 6, which is 94, 1 minus 1 over 64, which is approximately 94 minus 1.5, because 1 over 64 is about 1.5 times less than 94. So this is about 92.5. So you can do these more precisely, just this is a quick way of estimating these. So these calculations have shown that the optimal strategy would be to take 6 times, i.e. we let n equals 6, and the expected payoff when using this optimal strategy is about equal to 92.5. So that's the solution to the question. Thank you very much for watching and hope to see you in the next one.